Okay, hi, this is going to be a short video on how to build a calibration using your Drainac drain time assessments and your lab assessments, manual lab assessments of CSF, stock freeness. First of all, you want to collect data. This is an example here of data that has been collected. I'd like to draw your attention to a couple of things about it. First of all, I have what's called pre-sample data. Pre-sample data is basically collecting a couple of drain time analyses prior to collecting a bucket of stock. There's a post-sample as well. Those represent a couple of drain time captures after you've gotten your bucket of stock. And then, of course, you've got your bucket of stock, which you then subject to lab analysis. And I typically recommend that customers do split it into two and do them individually. Now, the point of going through all of this is to take into account the fact that the process is variable. It's not homogeneous. It's changing all the time. And as a consequence, you have to take into consideration the fact that because things are changing, you need to accommodate the data to take that into account. So we take a few drain time samples before and after. We average those together over here. And then we have lab samples. We average the lab samples as well. We do multiple lab samples, at least 2 and 3 and would be better, and 4 would be better still. But we want to do that because the TAPI 227 test is a variable test. It has a lot of corrections associated with it that have to be done properly. If Tom does it, he's going to get a different number than if Jack does it, so forth and so on. So what we're trying to do is we're trying to average out all that variability as best we can. In this case, I've got 4 drain times and 2 lab analyses, and I then average those guys together to basically get an average data pair. And that's what this average lab and average time 2 columns over here are all about. So that's data collection. All right, this is this Excel spreadsheet that I've got here is a standard Drainac calibration worksheet that's available to you. We're more than happy to email that to you. It has a few tabs in it that we'll go through. That'll help you take advantage of the calibration. First thing we want to do is we want to move this data into the actual data sheet. So I'm going to go ahead and copy this data. I'm going to move it into the so-called Recal Data tab. Oh, I've already had it there, but I'll go ahead and put it there again. Okay. So this is the first tab of the worksheet that you're going to have to concern yourself with. Basically, let's look at the raw data entry section here. It's the average lab samples and the average Drainac cycle times or drain times. Okay. We have 32 data points in this particular example. These 2 columns, the milliamp conversion and the log 10, these are intermediate values which are utilized in calculating some of these parameters over here. We'll get to that in just a little bit. Okay, the very first thing you want to do is you want to take a look at your data, see what it looks like. So let's go ahead and create a little scatter graph. So highlight the data that is of interest, come over here to insert and hit scatter graph, and it creates a little graph. This is incomplete. Right click, select data, edit the series, and we need to add the drain times as the X value. All right, and okay. Here's our data. Let's clean this up a little bit so we can see our data a little bit better. We don't need 2 digits of accuracy there. And I'm not a big fan of the default markers, so I like to change those. You can over here to format, and this little drop-down box allows you to identify the thing you want to format. In this case, this data series. and then you can hit Format Selection, and you can select anything you want. I like the circle. I like to color it in, and we'll keep it yellow and put a nice black line around it. There we go. Yeah, see, that looks a lot better. Okay, so that's this data set, and as you can see, there's a nice little trend in here. Now, the quickest calibration you can do is just to right-click on any one of these data points and select Add Trend Line. Now, there are a couple of different trend lines that you can select. It defaults to linear, but you could just as easily do logarithmic or exponential or polynomial, where you can change the order of the fit. I would avoid using that for the most part. Power, you just can pick which one that you think fits your data the best. For most work, linear is going to work just fine. Now, back to the quick calibration. So you've got the linear, that's the best fit line, and you want to look at the equation, and you want to look at the R-square. Let's drag this out where you can see it. Okay, that is your equation. That's your calibration equation, and actually this should be predicted CSF is equal to minus 5.0039 times the drain time plus 742.4. That's the calibration. It has an R-square of 0.5775, a perfect fit. If all these yellow dots were on this black line, that R-square would be 1.0. If the scatter becomes much more broad and less definite, this number drops. And the lower it drops, the less certain you are about your calibration. So you could actually take this equation, program your Drainac to output drain time as opposed to CSF, take the 4020 milliamp output from the Drainac and plug this equation in, and you would get predicted CSF. That's the quick and dirty method. It's not bad, but it's incomplete. For one thing, we don't have an assessment of what the 2 sigma is for this best fit line. So that's what we're going to do now is we're going to go through a regression. We're going to basically go through the long way of extracting this equation, but it will also give us some regression statistics, which we'll take advantage of as well. So let's make this small for the moment. And we'll go ahead and do a regression. All right, so doing a regression, you need the data tool pack from Excel. Plenty of YouTube videos on how to activate it in your version of Excel if it isn't already activated. If it is activated, you'll have this data analysis tab over here. So you just click on that and you select regression and say OK. And now we basically define the input ranges for our regression variables. So we want our Y variable, which is going to be the lab CSF values. And we want our X variable, which is going to be our Drainac drain times. All right. You notice that I selected the actual title of each column. That means I have to make sure that this labels value is actually selected, because otherwise it'll try to interpret that first row as numeric data, and of course it isn't. All right, so now I have a choice. That's the input for the regression algorithm. And the next question is, where do I want to output it? Normally the default is the new worksheet apply, but I prefer to do it on the same page here. So you click on it and you select a particular cell. So this one's pre-selected J16, which is probably where I had it before. That'll work just fine. And so we just go ahead and say OK. And whammo, there is our regression. Now the first thing I want to draw your attention to is the R-square. And you'll see it's 0.5775281999. Okay, well, that's the same as value over here that came from our little trend line exercise. The other thing, the coefficients, they're down here, and you'll see that the average drain is drain cycle time value for coefficient for the average drain cycle time is minus 5.003913.019, which is pretty much the same as what we've got there. And 742.4, blah, 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 that's the same there. So that's where this information comes from. The final thing that comes out of the regression that's really important is this standard error. The standard error is basically the average of the error. Looking at this graph again, you see this best fit line right here. Well, obviously these data points are not on the best fit line. So if you were to actually calculate what the average distance from the best fit line was for each one of those data points and then add those all together and then take the average of that, you would get this number, this 29.68. That 29.68, incidentally, is in the units of the y-axis, which in this case is milliliters, CSF. So that's your 2 sigma, 29.68. We are also interested in 2 sigma, which is twice that number, or 59.37. And we're going to use that here in just a moment. Okay, so now we have this regression. And I like to look at this stuff graphically, but let's talk a little bit about where we could host this environment, this regression equation. Well, we've already talked about if you want to host it in your DCS, which is programming this equation right here. Okay, fine. The next question is, what if we wanted to program it into the Drainac? Well, if we want to program it in the Drainac, we have to use these boxes up on the top of the worksheet. The very first thing you want to do is specify what range of freeness you want the system to be able to respond to. Well, if we look at our data, we see that the data runs from about 350 freeness up to about 550. If we plug those numbers here, and I just happen to have done that already, and you'll notice that there's a little tool tip when you do that. That's that little red corner that tells you what to do with that cell. So in this case, we're going to put a minimum value of 350 CSF with a maximum of 550 CSF. The system will now calculate your freeness values over here. So your freeness 0 is 350, and your freeness span is 200. So 350 plus 200 equals 550, and that's where that comes from. Okay, so that defines the y-axis. Now we have to worry about the x-axis. Well, this spreadsheet basically extracts the equation for this curve from the data and uses that information to interpolate, or rather extrapolate values for the time that's associated with this minimum and maximum freeness range. So here we have a 0 of 42.93 and a span of 44.61. If we were to change this range, say from 300 to 550, you notice that the 0 changed and the span changed, and also our time values changed somewhat. Okay, so you always want to keep track of that. Make sure that you don't lose that. So 42.93 and 44.61, these values are actually tied to the rest of the tabs in the worksheet. So the very first thing we want to do is go over to Drainac response. This is basically a calculation which is going to use the calibration that you've defined. So here's our 0 and span for the freeness. We got that from the recal data tab, and the 0 and span which we got from the also from the recal data tab. This value right here I just plugged in. You would just copy it. So you would just go Control C, put it over here, and right click and paste the value. Now I had already done that, which is why it didn't change, but that's where that number came from. These columns are basically given certain time values. It's going to calculate what the displayed freeness would be based on this calibration. It uses the 2 sigma values to add and subtract from the displayed freeness, so then we can then go over here to the C stands for chart underscore performance tab, chart underscore calibration tab, and that's what the calibration actually looks like inside the Drainac. So the solid red line in the center is the best fit line. You'll notice that it's curved, and that's because we're actually utilizing a logarithmic model inside the Drainac. The 2 sigma are the dash lines, both positive and negative. Now, the 2 sigma was derived using a linear model, so it's not exactly what it would be if it were an exponential model, but for most applications, it's going to be good enough. Okay, so what does that mean? What it means is that the best fit line here is what the Drainac is going to produce for a given time. 60 seconds, for example, is going to produce a predicted freeness of roughly 435 CSF. A analysis time of 50 seconds is going to produce a freeness of about 495, and so on. So that's what the Drainac's going to do. When you go and you get a lab sample, and you notice that the Drainac was producing 60 seconds or 435 CSF, and you grab that lab sample and you take it to the lab and you analyze it. What these dotted lines, and that 2 sigma was 59.37, by the way, and our square was 0.5775. What that 2 sigma is telling you is that 95% of the time you would expect that lab sample to be within plus or minus 59.37 of that value. So in this case, 60 seconds, 435. So you would be good basically from 435 up to 495 roughly, and down to 375 CSF, which is basically from this point up to about that point. Okay, 95% of the time you would expect your lab value to be in that range. Of course, 5% of the time you would expect it to be outside that range, or it could be outside that range, and 1 out of 20 times it could be outside that range, and that's okay. The calibration is all right. That's just what the statistics are telling you. If, however, you notice that you were consistently out of that range, or let's say that they were always on one side of the line, well, that might be a reason to go in and recalibrate. Now, the reason that the spread is so wide in the first place is just because the TAPI 227 methodology has a degree of uncertainty associated with it. This is just a fact of that test. You can do more averaging and attempt to try to reduce the variability. You can try to make sure that your people are processing those lab values as close to the TAPI 227 methodology to try and get that tighter and tighter. Basically, I think that if you were to do this absolutely perfectly, if you were to do a TAPI 227 test absolutely perfectly, instead of having a 2 sigma of plus or minus 60, you might get it down to plus or minus 30. Okay, so this isn't really all that bad. Okay, going back to the data, let's go ahead and put the rest of our calibration in here. The freeness 0 was 350, the freeness min was 200, and the time 0, 4293, 4461, 42.93, 44.61, I think that's right. Yep, okay. And that's our calibration, the Drainac calibration. Okay, we have what's also called a performance graph. Here This is the Drainac output getting converted into a predicted CSF. If we were to do that for this line and just do it for all the data points, it would look like this, where the Drainac prediction is actually on the x-axis and the lab estimate is on the y-axis. So it's a straight line, which is what you'd expect it to be. And here is the expression of the 2 sigma again. So this would be if the Drainac were outputting a CSF value, you'd use this graph as a means of assessing what's going on, because you could quickly look at what the Drainac was saying, what your lab was saying for any one particular data point. Okay, let's see. So we've covered it quick and dirty. We've covered hosting it in the Drainac, and we've covered the 2 sigma. I think that's about it. Thank you for your attention. If you have any questions, please don't hesitate to call us at TICO, 504-833-6381. Thanks very much.